So, good morning, everybody. This is the last day of the workshop. Time passes quickly here. Let me introduce the speakers. First, we have the cat Nina, and then Giuseppe Mingione from the University of Parma. The title of his talk is Nonlinear Potential Theoretic Methods in Non-Uniformly Elliptic Problems. Please, we look forward to listening to you.
Okay, how can I switch slides? Okay, so this talk is not about a specific result, but just it's going to give a set of ideas that are going to apply in a different setting of contexts, and that can be applied more and more in a unifying way for many problems. Of course, I will choose to give. So it's rather than on a specific result, is about a general method that you could use to prove regularity results in certain nonlinear PDEs. Of course, I'm going to focus on some specific problem. And in particular, I'm just interested in what are the best possible assumptions on external ingredient X and mu in order to guarantee that U is Lipschitz, that U is bounded, that is solutions are Lipschitz. But this is just one possible application. It's just because I want, at a certain stage, I have to focus on something, okay? And in particular, the main focus is on non-uniformly elliptic operators that Christiana already talked about. And Christiana's talk was more on a specific results. Now I'm more concentrating on a general picture. So let me start from a brief recap on uniformly elliptic problems. So uniformly elliptic problems I consider a very classical setting, the one fixed by Lancesca and Altseva. And of course, the main model example is the P-Laplacian operator with coefficients. So you can put coefficients that are elliptic, then you put this one here, and you put mu or something like this. And these are very standard, so I'm not going to comment a lot. So think of this equation, but think of any general equations modeled after this. Okay, so the idea is how to use nonlinear potentials to prove regularity of solutions. Okay, and about the gradient. So first gradient potential estimate was many years ago by myself, and this proves the following estimate. So what is the novelty in this equation is that this is the localization term that has to be there, because when R goes to 0, then you get du and u. This goes to 0. So this is just a constant. So what you get here is that you can pointwise estimate the gradient by the convolution via the fundamental solution. So in particular, when you are in Rn, this just works as the linear case. So this is a very surprising result, because essentially this is known, there's no difference between any general quasi-linear equation and the Poisson equation. So there's no difference whatsoever, because typically you do via convolution, because the problem is linear, this is the Green's function. But here you do for general nonlinear elliptic equations. So the outcome is that the whole gradient theory of these equations for p equal to 2 is completely trivialized, because if you want to know in which space the gradient belongs to, depending on data, then you simply look at the Poisson equation and there's no difference whatsoever. So the first consequence of this estimate is that there is no difference between any general quasi-linear equation and the Poisson equation. So for instance, if you want to know when the gradient is bounded, you just look at when this guy is bounded, and then you're done. If you want to know if when du is in a certain elliptic space, so it's Calderon-Zygmunt theory, you know what is the mapping property guaranteeing you that there is potential is sending you into this space. Yeah.
Is it a radon measure or
radon measure? Yeah, radon measure. But don't, okay, forget about the measure. Take a infinity function and take it as an a priori estimate, and then by density you can reach any space you like, because I'm focusing. So, but the first thing is that nonlinear potentials allowing you. Okay. What about the general degenerate case? In the general case, there is this theorem that tells you, even more surprisingly, that there's p minus 1 and there's no difference. So once again, this estimate is in some sense trivializing the regularity gradient theory of these equations, because any property you would like to have on the gradient, there's no difference between this equation and the Poisson equation. So in other words, you can act as there is a fundamental solution for nonlinear elliptic problems. And when you go to Rn, you are bounding like this. E minus 1 less than or equal than b mu y minus x n minus 1. This is in Rn. So all the estimates by people like Ibanez, Di Benedetto, Manfredi, Valenti, Occardo, and these people, they are all just implied by this unique estimate. You don't need to have any difference because this acts from the very beginning. Okay? So it's a complete, this is an example of how linear potentials, even nonlinear potentials are going. Okay, after this paper, there has been a tremendous, and a first result in this direction for you was given in this very fundamental paper by Piparangamali, but for you. For the gradient is a different story because you cannot differentiate equations when the right-hand side is a measure. Okay, so this is as far as the uniformly elliptic case. And you can even put this into an intrinsic way and write this. This is an equivalent form. Because A of du, so you see, it's like, how do you solve, think of these papers by Brexis, Bourgan, and whatever. How do you solve divergence of G equal to mu? You apply an I1 with potential. This is Bogowski's lemma. So this is an integration that cancels this, and then you get that G is estimated by I1F. Of course, this cannot be applied by the P-Laplacian because this equation is not elliptic and has infinitely many solutions, but still you can prove the estimate. And this once again trivializes the regularity theory for these equations. In particular, as just one of the many corollaries you can get, this is also a very long-standing conjecture of Uraltseva. So Uraltseva conjectured that the condition for which you can prove Lipschitz continuity of solutions of this on mu, or the external ingredient, is independent of P. And this condition is obviously independent of P because there's no P on the right-hand side. You see, the crucial fact of this fact is that P disappears from here. Forget about this, of course. P disappears. This now has been removed recently by Nguyen, Hong, and Pink and other people.
I have a question.
Huh?
So what you said about the divergence, so in general, if you have a divergence of a vector field given by this measure, you're going to get the same type of estimates, or?
No, you can solve. This is a Bogowski's lemma. So get me an equation like this, I can guarantee you that I find a solution with this kind of estimate. But this has nothing to do with that, because this is not elliptic and has infinitely many solutions. It's non-elliptic. Otherwise, you would have done the whole regularity theory by just a simple integration. But this is not the case. You have to go through that. But once you have this, all these estimates, I mean, all possible gradient estimates on the P-Laplacian operators are implied by this one, because you have a fundamental solution now. Okay, let me go on. This is a general fact because it's really linked to the divergence form in this case, but it's even more general. And this is a theorem of Baroni that tells you that if you have a uniformly elliptic operator, I'm going to talk about this later, then this holds anyway for any possible structure inside. And this even holds, and this is a paper that we had with Cusi and Totti, is here that if you have a fully nonlinear elliptic equations in Ln1, then you know that you have certain potential estimates. But let me come on this later. Okay. Okay, a classical theorem of Stein tells that if dB belongs to Ln1, then B is continuous. This is the borderline case of Sobolev-Maury embedding theorem. So this is the largest rearrangement in variant function space, guaranteeing you that B is continuous when dB belongs to. Okay, what is Ln1? Ln1 is prescribed by this decay at infinity of the level sets. It's an interpolation space. The second index is tanning the first one and actually describes logs. the first things you think about after powers. It's they are particularly useful to describe borderline situations when a certain log or a certain BMO type thing is crucial. Okay. Okay, an equivalent form of Stein's theorem is the following one, because these are interpolation spaces. So by Calderon-Zygmunt theory, from these you get that the second derivatives are in Ln1, and therefore du is continuous. This is an equivalent form of Stein's theorem, and this space is sharp at this stage. You cannot do better than this. Now, what can you prove about when you use potentials? You can prove the same. It's a nonlinear Stein theorem. And actually, we proved the same for fully nonlinear with Totti and Tuomo. For fully nonlinear, the proof is much easier because fully nonlinear equations are much easier than the P-Laplacian. You don't have to control the degeneracy. You just introduce this Pucci's operator and then you linearize. But for the P-Laplacian, you have to control all the way down the degeneracy. In fact, the natural equations are usually coming up in divergence form. And so once again, this is no difference. And this is another manifestation on this old conjecture of Uraltsev, who stated that the sharp condition on the right-hand side is independent of P. And you see, this is fully intrinsic condition. There's no P there. Right-hand side, you don't see any P. Okay. Now let me go to the non-uniformly elliptic world. In the uniformly elliptic world, let me just concentrate at the first moment on functionals. I'll tell you why later. But of course, the catch between functionals and equation is usually the Euler-Lagrange equation. So it's so let me tell you that it's better to concentrate on functionals not because of the a priori estimates. There's no difference at the level of a priori estimates or of regularity estimates between minimizers and functionals, because in fact, you prove estimates for minimizers using the Euler-Lagrange equation. But in the approximation procedure that you have to use in the non-uniformly elliptic setting, having minimizers is more. Let me go on. Okay. So what is ellipticity? Ellipticity means that the first derivatives or the second derivatives here are controlling and controlled by two functions, and I'm putting here, and this acts as lower and upper bounds on the eigenvalues. So think G1 and G2 by two eigenvalues, as two eigenvalues. This will, I'll go fast on this because Christian explained this very well, much better than how I can do. And so these are the lowest and the highest eigenvalue. Okay, so uniform ellipticity means, okay, there are several conditions by uniform ellipticity. Usually the idea is that you want to have that this quantity is always bounded. Because when you prove estimate, this is the quantity that comes up at every stage. So if it's bounded, then you are in the uniformly elliptic setting. But since I'm interested in Lipschitz estimates, so I'm interested to exclude the fact that the gradient is large. So I'm concentrating only when the gradient variable is large. So prescribing every condition when the gradient is large. And of course, okay, this is the uniform ellipticity. Non-uniform ellipticity is when this there's at least one point when this fails. It's as simple like this. At least one point because I'm considering continuous coefficients. So 1 point means a lot already because coefficients are continuous. But anyway, when you are not able to control this quantity, then you are in the non-uniformly elliptic setting. This is a very classical. This is a very classical topic. So Gilbert studied this a lot, even Finn, because they stem also from minimal surface equations. Stampacchia, there's a lot of Russian literature, important and overlooked Russian literature on that. Schrödinger's thesis was on these things. There's an old paper by Leon Simon, a very deep paper using this. There's this like Jeska and Uraltsev, where they extend this the Giorgi Pombieri Giusti theory and Pombieri Miranda Giusti theory and the Giorgi's theory and so forth. This is a classical things. More recent papers are by Schrödinger, Zhikov, two overlooked Russian genius that was producing very many papers on homogenization. And I mean, there's this book by Zhikov, Oliening, and Kozlov. I mean, they did fantastic results on homogenization much before. I mean, results that nowadays people are rediscovering independently after 50 years or whatever. And then Ivanov has a monograph where he summarizes all the progresses in this St. Petersburg school, and then Marcelling, you put this in the setting of calculus operations. But let me go on. So okay, and so this I call the ellipticity ratio, and this is G2 over G1. So this is what I call the ellipticity ratio of the operator. So when this goes to plus infinity, you are in the non-uniformly elliptic setting. So what's the difficulty? The difficulty is that you want to exclude that the gradient blows up, okay? Because when the gradient is bounded, then the problem goes back to the realm of uniform ellipticity. On the other hand, what you use to prove that the gradient is bounded in the standard setting is that this quantity is bounded. On the other hand, this quantity is going to plus infinity when the gradient gets large. So there's a competition between the two. And this competition is usually solved in this classical literature. I told you by prescribing that this ellipticity ratio is blowing up as a power with Z, but this power cannot be too large. So if you look at these classical papers by Serin, Tuldinger, Lagishevsky, and Altseva, in a way or in another, they always go back to this fact. You can blow up, you can allow blow up in the gradient of the ellipticity ratio, but this blow up cannot be too large. Otherwise, you cannot control things. And this is you cannot solve this competition, right? And typically what you do in the polynomial setting, you say that one eigenvalue grows as the P Laplacian one, and the other eigenvalue grows with a different power, so that you can bound this as a ratio. So this is a typical occurrence. So they are growing with two different powers. So why I call it P minus 2 and Q minus 2, it's because in analogy with the Laplacian. Okay. In fact, this is the standard, the PQ terminology introduced by Marcelling. When you start from a function from PQ, and then you get that the second derivative scale accordingly with the growth. Okay. And this Marcelling was also motivated by problems in cavitation, where he did a model for cavitation via relaxation that, in my opinion, was better than other models considered at the time, was overlooked.
So Rosario,
Yeah.
no assumption on how big the P and Q are.
Wait. Okay, in all the literature, this should be small.
Ah, okay.
So Q cannot be too far apart from P, because otherwise there are counterexamples. Because you cannot allow that this ratio is growing too much, otherwise you break this competition in favor of the irregularity, and there are counterexamples, right?
Somehow integrable.
Yeah, it's I mean, it cannot be too, otherwise there are counterexamples, and this is necessary. Okay, for instance, examples, you have a slow perturbation of a power. You have this example was cooked up by Talenti. You have different powers with respect to growth. You have the classical isotropic when this comes along in elasticity, where there are different directions in reinforced material. So you stiff with a material with in a certain direction, and then you feel a different hardening exponent in that direction, but not in the other. So it's typical examples like this. So these are just examples. They were first considered by Altseva in a forgotten paper by many years ago. And then we discovered. Right? So, and even you can allow these kinds of functionals. And they were considered several times by Ducanel, Lieberman, Marcelling, Evans in the setting of KM-AM theory. And these functionals, for instance, he wanted to approximate the infinity Laplacian with these kinds of functionals with exponential growth that are better. So philosophically, it should be easier to prove that minimizers are Lipschitz, because you are approaching the L-infinity norm in which every competitor is Lipschitz by definition. But in fact, it's much more difficult because the ratio between the eigenvalues is not even growing polynomially, but exponential. These are very difficult to handle. Okay, let me just give a model result by Marcelling, but this is just a model. So non-degenerate for simplicity. So this grows like P, this grows like Q minus 2. The ratio therefore grows like Q minus P. And if you have this bound, then you get this estimate. This has been recently improved by several people. But the point is that this Q over P cannot be too far apart. So the basic condition is Q over P, like this. The optimal bound is not known, and there are several people even improving these kinds of things. And this is just a brief survey of recent results on the topic in this polynomial growth. But it's always the same. You see, personally, I'm not a fan of getting the best bound, but just the best asymptotic, because the best bound can be probably determined by looking at specific multiples. But the asymptotic should be always this one. There's no way out from that. Okay, now let me go back to this theorem I showed you before. This is the nonlinear signs theorem by Husi and myself that tells you this. So the idea is that we have, and this can be also extended to fully nonlinear elliptic equations. This we did with Totti and Tuomo. And this reaches the borderline case of results of Caffarelli, Tulinger, and other people. But the proof of this is much more delicate. And so the idea is that what happens in the non-uniformly elliptic setting is the right-hand side a universal condition, because the idea is that this should just depend on the shape, because if you look at these equations, so whatever is this, you should be able to commute by regularity or Calderon-Zygmunt theory into a statement of the derivative of this. Because when you prove regularity, this is what you're doing in Calderon-Zygmunt theory. You're commuting the divergence with the gradient. So something non-elliptic in something elliptic in some sense. And then you're recovering the full derivatives. So is this universal? And okay, now let me go on the first result I'm going to talk about. And I'm going to consider just a minimizer of a functional like this. Well, U is the datum, so that the equation looks like, the Euler Lagrange equation looks like. Yeah. Okay, these are the two eigenvalues, and the assumptions I put on the two eigenvalues is that G1 over G2 is controlled by a power type of this quantity. This quantity looks odd, but it's a natural quantity that is implied by this lower bound in terms of coercivity of the function. And a sample result is that this condition is universal. This condition is universal because you can prove this a priori estimate of minimizer. Here you have the energy, which is finite. Here you have the ln1 norm, and here you have an infinity norm. This looks odd just because it is very general, because it's going to get all possible things together. But it's actually when you commute this into the PQ setting, because G1 and G2 can be anything. So this even catches the case of exponential growth functionals. And in particular, there are very interesting developments done by Bell and Schaffner recently, and by De Filippis and Piccinini, that extend this to Bell and Schaffner improve certain conditions in the PQ case, and De Filippis and Piccinini go up to the boundary in a very sharp way. So they prove boundary regularity. And okay, what is the idea is that we extend this nonlinear potential theoretic approach to the non-uniformly elliptic case. And then we are able to catch, when f is equal to 0, all the previous results plus other estimates. Let me go back to the shape, to the very specific shape of this estimate. So in the PQK, in the exponential case, you get the G1 grows like an x of t something, or x by x. In the PQ case, GT is t p minus 2. So this goes like TP minus 1. When you integrate, this is due to the P. And in fact, that estimate in the PQK, when P is equal to Q, so you go back to the uniformly elliptic setting, that estimate gives you back the sharp estimate for the P Laplacian case. Otherwise, when you have P and Q, then you get exactly the same Cialdini's estimate. So that estimate catches everything. You just have to specify G1 and then you get all these things. You know, this is sharp because you cannot get better than ln1. Okay. You can have a full result with exponentials and conditions in a recent paper by De Filippis and myself. And you can relax a lot, all kinds of assumptions. You can put Sobolev coefficients. So you can even say that coefficients are not regular and with some d larger than n. So by embedding, these are Hilbert continuous, and this is minimal in this setting.
What is the, sorry, what is the significance of P? The exponent, okay, I saw it, sorry. The exponential includes the dv to the P. Sorry, I didn't see that, the parenthesis. And I said, what? Yes, right.
Otherwise, I mean,
Yes, exactly.
it's like they
Yes,
take C1 and C2.
yes, exactly.
Okay, and then this is also optimal because it's in general false when d is equal to n because coefficients are not in the right space. So, and once again, this can be done by using these nonlinear potential theoretic methods I'm going to tell you later. And then you can go on and put any combination of the exponential, there's no difference whatsoever. So this is just to tell you that this kinds of approach is going to give you sharp results at any level and to treat globally all kinds of possible things. Yeah.
These results are not contained in that G2 over G1.
Yeah, they are contained over there. Right.
Okay, so there are results of that also.
No, G1 and G2 now depend also on X. As I told you at the beginning.
But can you also show this when they have dependence on X?
Yeah. This is done in the first slides. I mean, when the functional is not autonomous, then there is no X here. Otherwise, you put G1 and G2 depending on X because the eigenvalues change from point to point. And you see, this is very, very delicate. Why it's important to understand the dependency on coefficients here? Because this is an exponential. So you see, you know that if a function satisfies this, if you multiply here by a constant, this is not true anymore if the constant is larger than 1. So the variability of coefficients inside an exponential is far from being a perturbation in the perturbation setting. So you have to find a very rigid approach via nonlinear potential theory to treat these kinds of things. And in particular, you can go back to the uniformly elliptic setting and finding something new even in the uniformly elliptic setting. So for instance, this is again the case of the P Laplacian. In the case of the P Laplacian, Hus and myself, we proved that this has to belong to ln1 and this must be Dini continuous in order to get a du bounded and continuous. So Dini is sharp. It's a sharp modulus of continuity. There are counterexamples otherwise. Here you trade Dini continuity with this condition. So both the derivative and f must belong to ln1. And this is completely new also in the uniformly elliptic setting. Okay. Just let me give you an application to obstacle problems. Now you want to minimize any functional p, q, exponential, whatever you like, with the obstacle. And then if you want to know what is the sharp condition on the obstacle, guaranteeing you that the u is locally bounded, then this is the condition. This is a simple application of these results. Dimensionally speaking, it is coherent. Because the obstacle problems can be written in the following way. So this is totally standard in the case of the Laplacian. You can do it by hands. In the nonlinear case, it takes a bit more difficulty. You need Riesz representation theorem because it's nonlinear. But you can turn an obstacle problems into the divergence of this guy. And this is a function which is supported on the contact set. And so this is exactly what you expect, right? Because when u is equal to phi, then you know that the gradients are almost everywhere equal, and therefore this is identity. Otherwise, it is zero. Of course, at this level of generality, you don't know how good these sets are. Of course, are open by, but this is what you get by the Riesz representation theorem. Now, if you call this f, the second derivatives in ln are in ln, so they are bounded in particular because of Stein's theorem, and they are in ln1. Because you see, you differentiate, this is bounded because by Stein's theorem, the second derivatives are in ln1, so this is bounded, this is bounded. You get that the right-hand side is in ln, you apply the previous result and you get the result. And this works in full generality for any obstacle problems with bad coefficients, bad growth, and whatever. It's a general result. So this is contained in this new paper by
Is this sharp too?
Of course. I mean, I wouldn't expect that this is because it's sharp for the Laplacian, you know, say, because for the Laplacian, this is sharp in ln1. I wouldn't expect that this is not sharp. And this is the standard space. You cannot get better. There are counterexamples by Chunky telling you that ln1 is the largest rearrangement function space for which this can be true. Okay, so shots from potential theoretic methods. So let me just give a few ideas on how these things can be done. Of course, I will skip all results and technical points because otherwise we do not finish. So the ideas are mainly taken from these three papers, and especially the last one, that was presented by Christiana, where we solved this long-standing problem of Schauder estimates in the non-uniformly elliptic case, because the Schauder theory in the non-uniformly elliptic case stops being a perturbation theory. That's the point. Stops being a perturbation theory. And stops being a perturbation theory because if you think of models of this type that are still pointwise uniformly elliptic, pointwise, but weaker non-uniformly elliptic, then there's no standard growth is just given by the coefficients. So if coefficients are generating a form of non-uniform ellipticity, then the coefficients cannot be a perturbation. Okay, so for a linear elliptic equation, everything is known. This is the Georgi-Nash-Moser theory. How do you prove that solutions are bounded? You take a solution and you want to prove. Okay, you write down this Cacciopoli typing equality on level sets. This is b minus k plus is the maximum between b minus k and 0. So you cut. The only difference, you have to be careful about the scaling, but this comes from the scaling because you see this is a second derivative, this is 1, and you get double of the radius. But this you can trust me, this is the Cacciopoli inequality. At least without f, this should be very familiar. Okay, then you start iterating. You start iterating because from this is the Cacciopoli we're talking about, and this is, you see, this is r squared because if you scale back, then the right-hand side scales like r squared. And then you run the Georgi's iteration. That is, you gain an exponent, you start a geometric iteration, and then you end up with being bounded, and then you get this estimate. Okay, now let me go to Lorentz spaces. So the first point is the classical Cacciopoli inequality. The second point is the classic of the Georgi's iteration. Okay, now these are Lorentz spaces. Okay, as a first approach, you just take this as an abstract art, but you don't read exponents and blah, blah. But this is what it is. But they work. This is okay. This is the rearrangement invariant version for those who like rearrangements. This is the level set decay version for those who like level sets, but they are the same via for beams. But this is what it is. For p equal to 2, for gamma equal to s, this simplifies, and this is nothing by Lebesgue. Basic properties. The first index dominates because this refers to powers. This refers to logs and all kinds of logs. And the reverse, this goes in one direction, this goes in the other direction. And by the way, there's a different form using maximal operators to express the Lorentz norm. This is the maximal operator only when S is larger than 1, because maximal operators are bounded only when for P larger than 1. Okay, this is what it is. Shot number 4. These are the general nonlinear potentials we are going to use. They depend on 4 parameters. So why I do put 4 parameters? Because all 4 parameters are needed if you want to catch a unified approach for everything. They go back to the basic work of Having and Mazia. This is a these are the potentials. So why they are why I call these quantity potentials and why they are important. Okay. One thing, mapping properties. When this is true, then this is true. So this object is bounded when the Lorentz norm is bounded for F. It's a computation. I mean, nothing very difficult. It's a computation. Trust me, this is, and you need all the parameters if you want to have a general approach. Okay. This is in L infinity, and this is Lorentz. So this is just a mapping property that telling you that this operator acts exactly like this. So the idea is that get me F when F is in this Lorentz space, and this is bounded. Okay. This is an extension of Kilpelainen and Mali, the George's iteration version. Okay. Then we prove this lemma. This is larger than 1. So this looks like a reverse Hölder inequality. If you look at this, plus a remainder. Okay. In particular, if you start from the Kachapon inequality, you apply Sobolev embedding, you get this. Well, this is Sobolev embedding exponent. Okay, and then what you get, if this is true, any function for which this is true, then this is true. In particular, if you know that this is in L infinity, this is in L infinity. So this is a pointwise version. So you see, in the George's iteration, you start from B1, and you stop to B1 half, right? Now you go all the way down to 0, to 1 point. You get a pointwise estimate. Okay, take it as it is. It's a remark. Okay, it's a 2 pages remark, 2 pages and a half, but it is what it is. No, but this is, it could also be worse. It could always be worse. Okay, now, look here. Okay, the approach I'm going to tell you is not sharp in low dimensions. You should still modify it, but this is just a presentation, so I can skip dimensions 2, 3, and 4. Okay, and 2 for the gradient, but this can be adjusted. But it's just for giving. Okay, now take this Kachapon inequality that I told you, that I showed you. Okay, now apply Sobolev embedding theorem, and this is what the Georgi does actually. And then you get this. Apply the previous lemma. Now you are in the range of applying the previous lemma. Apply the previous lemma. And spoiler. Apply the previous lemma, and then you get this. Just by the previous lemma. Okay, now prescribe that this is in ln half. If this is in ln half 1, it's Lorentz. This is bounded, and then you get the sharp result of Talenti and other people in a local fashion. So so this method in the basic uniformly elliptic setting gives you back what you already know, okay, in a sharp way. if you look at these papers by Talenti, actually, also you should look at some papers on Mazia before. This is the result.
There's a squared missing.
Eh?
Squared missing.
Where? Here?
In F, n over 2, 1.
Ja. No. It's P 1 over P minus 1. It's okay. It's okay. ln 1. Yeah, for the V, it's okay. This is okay. Okay, and now we do something that you never do, because this is something that I have to say, after many years doing regularity, I was surprised by. Now we do something that is never done when you use this estimate. You look at the dependence of the constants. Usually, when you prove estimates, you get, okay, there is a constant, and then you go to another constant. You can compute everything, but everybody knows that this is irrelevant. Okay, look here. Now we carefully look at the dependence of the constant. This was suggested by me, of course. The previous lemma can be stated in the following way. So you put a constant here and a constant here. Okay, and then this is what you get. So if you carefully prove the lemma, if you really are sharp at every point, you know that this is the dependence of the constants. Usually you see what you do, you throw away and put this is C. So you put this here, you put this here. But here we keep. Okay, keep it here. Okay, and now let me give an application to non-uniformly elliptic problems. Okay, to non-uniformly elliptic problems. In the simplest case, PQ setting. Okay. Thank you. Assume that du is in L infinity, is bounded by M. So this is now a free parameter. Then you can write down this Cacciopoli inequality where G of du is something like du to the p. It's hidden near the full strength of so-called Bernstein method, because Bernstein method tells you that if u is a p-harmonic function, then du to the p is a subsolution of a linear elliptic equation. Okay, and then here you see the typical Cacciopoli inequality satisfied by subsolutions. Okay, assume that this is not here, and this is not here when this is uniformly elliptic, okay? So this is the standard Cacciopoli inequality satisfied by subsolutions, okay? And now you encode the non-uniform ellipticity here. Why? Because you want to go back to something which is completely homogeneous, to which nonlinear potential theoretic method apply. And you pay the price of a constant that depends usually on what you want to prove to be bounded. So what you do, you are renormalizing a naturally non-homogeneous Cacciopoli inequality by plugging this constant out. And of course, at this stage, you would run into troubles if you just apply the usual methods, because you would get a constant that depends on on something you don't have information. But now we apply, and okay, in the PQ setting, this is this. What is this? In the general setting, G of t is nothing but this, the function I showed you before. In fact, for those problems, this is a subsolution. This is Bernstein method in the non-uniformly elliptic setting. In the P case, this transforms into this. So you see, what is this? If this is not here, if Q is equal to P, if you carefully look at the history of regularity theory, what you prove is that u to the P is a subsolution of a linear elliptic equation. So it solves, it satisfies the Cacciopoli inequality, and that was it. But now we have this guy here. And now the magic fact appears because you apply the previous lemma with M with the strict dependence of the constants. M here, and you apply the previous lemma with this choice. And now you start seeing why you need all the parameters, because the more intricated are the problems and the more parameters you need to get a unified setting. Okay, now you apply the previous lemma, the previous iteration lemma, which is this one. We have constants here and constants here. And then you get this. You get this. But this is still not good because this is the L infinity gradient. Okay, but now you do a covering argument in the sense that you take B1 half, you take 2 slices, and you apply this on small balls depending on this size. You do a very delicate covering argument at this stage. You take τ1, τ2. You apply this on τ1 minus τ2, and you get this. And you apply this M with the maximum of the gradient. So you cover it and paying the price of something which is blowing up. And observe that you have already bounded this potential with ln1, because if the right-hand side is in ln1, then this implies that this potential is bounded. This is the previous lemma. So you are using at this stage the potential to get information from the right-hand side. And now you get this. And now you want that this, you hope to reabsorb this, but this you can do if this power is strictly less than P, if this power is strictly less than P. So you prescribe this. And now you apply this iteration lemma of Jacquin and Justin. And then you get this. So once you get this, you do Young's inequality, because this power is less than P, and this power is less than P, you get this. Beta 1, beta 2. Now you apply this lemma, and then you prove the inequality you like. So that the gradient is bounded when the right-hand side is in ln1. And when the right-hand side is not there, this is exactly the bound by Mercalli. So at the end, so this is okay. So what is the point here? What is the information? You have used just a uniformly elliptic equation technique to deal with non-uniformly elliptic equation, because you have plugged out the gradient. You have plugged out the gradient. Plugging out the gradient, you have acted with a homogeneous estimate, which is typical of uniformly elliptic problems, but with the blow up of the constant. So the whole non-uniform ellipticity can be reduced to showing an explicit dependence of the constants. And this is something which is very uncommon in regularity. That is a structural thing of the problem is hidden in the dependence of the constants. So there's a very rigid mechanism here. This is a universal fact. In fact, you can prove even things when the equation is not differentiable. How do you prove that U to the P is a subsolution? You take the equation, you differentiate the equation, but if the equation is not differentiable, then you go to fractional spaces. In fractional spaces, you replace second derivatives by the gradient by fractional derivatives of the gradient. So you use Bernstein's method in the setting of fractional spaces. And you get a Cacciopoli inequality of this type, where now this will be certain exponents. I cannot enter into this is the paper with Christian, it takes 50 pages, but the idea is that you get, instead of derivatives of U to the P, fractional derivatives. Now this is very common because of fractional problems, but this was pioneered in 2 papers that were going out in the same year, 2006 and 7, one is by myself, when I used for local problems, and the other one is by Caffarel and Basseur. And then after this very popular stuff on fractional problems started. So you get a fractional estimate for this object, with certain exponents. I mean, now I cannot really go into the detail. And after this, you apply fractional Sobolev embedding theorem, and you get once again previous inequality. And now there's not only the contribution of this, of the right-hand side, but also the contributions of coefficients. And now there's a fourth parameter in the potential. Once you get this, you can go on with the explicit constant thing. So this is a very universal fact. So you can reduce non-uniform ellipticity, the dependence of the constants. And finally, something that can be done with the geology can also be done with Moser sometimes, but only sometimes.
Georgie.
Yeah, and for the pleasure of the American audience, I now would like to give a version of this using Moses. Okay, model result. I have a functional, no right-hand side, only coefficients, differentiable coefficients. And I want to show that this bound, which is sharp, implies that du is in L infinity log. Now, and this is from another paper with Cristiana. Now, let me show you how to get a fast proof and how to reduce any non-uniformly elliptic equation with polynomial growth to a uniformly elliptic one via sharp constants in the Moses iteration. Okay, first of all, you go back to the case P equal to Q. Q is everything is known, at least to experts. You run the Moses iteration, and you show that if this is the largest eigenvalue, you can always renormalize in the sense that the first one is 1 and then the second is L. If this is the largest eigenvalue, this is the dependence in the Moses iteration. This is the classical L infinity LP estimate, and this is the dependence on the eigenvalue. Usually, you see, this is thrown away. Okay, it's there, you just put there. Now we keep it. Now we keep it. So you see, so the idea is that you have a non-uniformly elliptic equation. So you imagine, you think of Leon Simon's papers or Marcellini papers, there are 20 or 30 pages of estimates to deal with this. Now you just plug it, put it there in the dependence of the constants. So it looks too cheap, but at the end it works. Okay, now this is, if you do carefully things, then this is what you come up with. You have to be very careful, but this is what you come up with. Okay, in a classical proof. If you redo the proof in a proper way, so directly and okay. Now, if you are dealing with an equation, Z will be the gradient. So you can reformulate on any ball the growth conditions in the following way. You have Q minus 2. So you write down as Q minus P plus P minus 2. You plug out as the L infinity norm. And then you can always assume that you are dealing with these special growth conditions when you're dealing with this equation. Because you're dealing with an equation and you know that the gradient is bound. So you see, this is the, look at the upper bound on the eigenvalue. Write it down here as Q minus P plus P minus 2. Plug out Q minus P, and then you get that you can argue under this condition. And now you get a problem, a uniformly elliptic problem, whose largest eigenvalue depends on the solution itself. Now, what you do, you use the previous lemma, you run Moses iteration, with the new dependence of the constants, it's not L, it's L times this to the N over P. This is what I showed you before. And now you want to prescribe that this object, Q minus P times N over P, is less than 1 to reabsorb. You do Young, but this is exactly the bound which is known to be sharp. So you do Young, you do this. And once you do this, you apply the iteration lemma. And then you get this, which is nothing but this, when P is equal to Q. So what you do, you take any non-uniformly elliptic problem, you introduce potentials if you have coefficients on right hand side, or you just track the constants, and then you run this procedure in order to renormalize the problem, to get it down to a uniformly elliptic one, paying the constant, paying a price of a constant that depends on what you want to bound, but at the end, everything fits if you follow this method. And so in particular, if you look at this old literature, starting from Lagichenski and Orialza, going up to Macellini, these are, I mean, several pages that can be summarized in the following thing. It's really hidden in the dependence of the constant. That is usually the point which is always overlooked by people who do regularity. We never care about how constants depend and on what, because actually it is almost always useless, but this is the case, but this is not the case in this situation. Okay, Nina says we can rest now.
Thank you for an interesting and vivid talk. Are there any questions or comments? Ladies first.
So I have two questions. One question is, what about systems?
This works for systems too, provided you have Uhlenbeck structure. It's written in this slide. I mean, it's already in this paper with Christiana. With Christiana, we do just systems, in fact.
My second question is, how about infinite Laplace?
I don't know.
The reason I'm asking is because there is this.
I mean, Evans used this exponential functional to approximate L infinity Laplacian, but I don't think that this can be.
No, I was asking because I had an important problem that Thurston posed, which has to do with the system, like it's related to a system that actually
this works
like infinitely.
I mean, it works with systems because we in fact use Bernstein's method. That is, we use inequalities on these kinds of things and on these kinds of things, and we use directly even in the fractional case. In fact, for p equals to 2, you can even go down in using.
So in this application you mentioned to the obstacle problem, I was wondering how important was the structure that it's coming from an obstacle problem? Did you use?
What do you mean the structure?
I mean, did you use that U is larger than psi? Really? Is that
no? No. What you do there is that this is a linearization procedure that was introduced by Dutzer in '84 in the setting of geometric obstacle problems. In the vector valued, and of course you have to use U larger than phi to get the variations. It's a delicate procedure. It takes 1 page, but it's based on Riesz representation theorem. Because you take a certain variational inequality for certain positive variations, and then you get that this is a positive functional because of the obstacle. And then by Riesz, there is a measure, and the measure is concentrated exactly on the contact set, and it has that form.
yeah, so
The interesting thing is that I checked it because this is not usually done. We require that the second derivatives of the obstacle belongs to ln1, which is of course smaller than ln. And this procedure works until this is exactly in ln. As long as the
I mean, after reformulation, you don't assume that.
you don't assume anything. No, and just this. No, this is because this is done in measure.
Yes.
This is not pointwise. So this is done in measure using integrals, and then it's just a weak formulation, and then you use Riesz representation, and then you check some convergence, just seeing some things that are integrable, and then this is the condition. This is not usually, okay, this is remarked in the paper. It's not written because otherwise, okay, the paper is already 85, but otherwise it would have been too long, but this is the condition that you need. So you don't use, so for instance, for the Laplacian, it will be very easy. But in this level of generality, it's not difficult, but it takes still 1 page of computations.
So there was one more question.
Thank you for your talk, Giuseppe. I think one of the reasons that you could cook all these estimates was because you had some sort of uniform dependence on gradient of u for the coefficient and x. So the thing is, if you have,
No.
I mean, if you have dependence on u, something like
No,
medium,
dependence on you. Okay.
then you cannot do this. And also, if you don't have divergence form,
No,
if you
I
want
think
to
you
work
can
with-
still you can still have something like that.
How
It's in
could
the
you
paper
work
with
with it?
Cristiana. Dependence on you. It's in the paper that Cristiana showed.
Non-divergence?
Huh?
For non-divergence?
For non-divergent, but I'm not talking about non-divergent.
Because
Yeah, I mean, I said if you have something like prismedium and if you have some non-divergence form and you want to work with viscosity solution, then these ideas may not work. So is there a way to get
Okay,
rid of-
I'm not assuming that these ideas are working in general relativity, for example. But I'm not dealing with general relativity. Let's say. I'm already happy with this, and if someone wants to get more, it's okay.
Monforte wanted also to say something.
No, I wanted to ask you, if you put some boundary, I mean, first, very nice result and talk. And second, I wanted to ask, if you put some, I don't know, Dirichlet boundary condition, for instance, you think you can find like absolute bound on the gradient, like,
Cristiana did with the there's a recent very long paper of De Filippis and Piccinini. I think it's on International Research Notices 22, where they do this up to the boundary under the most general possible conditions.
You can also extend to exponentials or.
So whatever.
I mean, it'd be cute just because that would open questions somewhere else.
yeah, but my question was, can you, in the estimate, can you remove the dependence on the gradient in LP? L infinity less than LP?
What do you mean? L infinity less than LP? L infinity. Oh yeah. This you can usually do, because then by minimality you can bound the u to the p with the data, and then you get a global estimate.
Okay.
I don't think you find this in our paper, because our paper is even more general and considers boundary condition only on a portion of the domain. But if you can put the same boundary condition on the whole domain and you use just minimality, then you get rid in a standard way of the boundary data.
Yes.
Okay, I don't have a question, but I have an infinitesimal protest.
Oh.
You said that in the Moser iteration, the normal way you do it, you don't care about constants, but that's not totally true. You need to keep track of it so that a certain series doesn't diverge.
No, you keep track of the constants as long as the exponents are blowing up, but not on the eigenvalue.
Okay.
And
Well, then I suggest that we thank the speaker again.